Okay, Assalamualaikum and morning or evening, everyone. Today, we would like to present our group project title is Prediction of Piston Rod Expansion using Mathematical Sequence. This presentation is prepared by Samsung Group. So, our group members my name is Muhammad Arish. This is my another team is Haziq, Adam, and Samsul. Each member contribute to calculation, Excel graph, and the preparation of this presentation. Okay, so we continue to problem statement. In internal combustion engine, the piston rod is exposed to repeated heating and cooling cycles. Due to this process, the piston rod expands over time. Continuous expansion may cause the rod to exceed the maximum safe length. If this limit is exceeded, can result in engine failure. Therefore, mathematical models are needed to accurately predict the expansion of the Princeton Road and prevent possible damage. Okay, let's go to given parameters. For this project, we are given several parameters. The initial road length is 104.0 mm. The constant increase per cycle is 0.4 mm. The growth ratio is 1.004. The maximum safe length is 110.0 mm. The cycle number is variable. Okay, these values are used to model the piston road expansion using mathematical sequence. So continue to the objective. The objective of this project are to apply arithmetic sequence to predict piston road expansion, to apply geometry sequence to predict piston road and piston road expansion, to determine the cycle when the road become unsafe, to compare smaller predicts failure earlier. So that's all from me. I will pass the next presentation to my friend.
Assalamualaikum and hi everyone. My name is Muhammad Hazir Azri bin Muhammad Razi. Number matrix AA251329. And I am from group 9. So today I will discuss about fila table and arithmetic sequence. For the fila table is the first one is facts. Initial rod length is 104 and 0 millimeters. Rod expands every cycle and maximum safe limit is 110 and 0.0 millimeters. For the ideas is use arithmetic sequence for constant expansion, use geometric sequence for proportional expansion, and compare both models. For the learning issues is what is the formula for arithmetic sequence, what is the formula for geometric sequence, and how to identify unsafe cycle. For the action plan is apply sequence formulas, calculate manually and using Excel, plot graph for comparison. Okay, so for arithmetic sequence calculation is in this analysis, our team evaluate the thermal expansion of a piston rod using the arithmetic sequence model. Based on the parameters assigned to group 9, the rod begins with an initial length A1 of 104.0 millimeters and expands by a constant value D of 0.4 millimeters during each operating cycle. By deriving the formula for the nth term, Tn is equal to I1 plus open bracket n minus 1 close bracket D. So we determine that the rod reached its maximum safe limit M of 110 and 0 millimeters exactly at cycle 16. Furthermore, using the sum formula, we calculate the total cumulative extension after 15 cycles to be 1602.0 millimeters. These results demonstrate that under a linear expansion model, engineers must schedule maintenance before the 16th cycle to prevent critical engine failure. In our analysis of the arithmetic model for group 9, we have utilized Microsoft Excel to visualize the linear expansion of the piston rod over 20 cycles. We observe that the Tn versus n graph displays a perfectly straight line originating at our assigned initial length of 104.0 millimeters and rising at a constant gradient of 0.4 millimeters per cycle. To access the mechanical safety of the system, we plot a horizontal reference line at the maximum threshold M of 110.0 millimeters. Through this graphical representation, we can clearly identify that the piston rod maintains safe operating parameters until cycle 15, after which it intersects the safety limit at cycle 16. This linear trend confirms that under uniform heating conditions, we can precisely predict the point of material failure, allowing for proactive maintenance scheduling before the rod exceeds its design tolerance.
Hi and Assalamualaikum. So now I'm going to talk about the rest of the content from this presentation. So today, now I'm going to talk about the methodology of doing this assignment. So what we use is using arithmetic and geometric formulas so that we can calculate the expanding and contracting piston rod from the combustion engine that we are trying to calculate. And we also perform manual calculations and construct table for 20 cycles for further investigation on how this repetition cycle works. We also plot graph using Excel so that we can compare results with safety limit so that the piston rod will not fail and possibly causing damage to the entire engine. So in the graph you will see the two graphs actually, which is Tn versus N and Sn versus N with a safety line. What is this safety line for? It is for if the extension exceeds the maximum safe limit, the piston rod will fail, possibly causing damage to the entire engine. So that is why we need to see where is the safe limit for this expansion of the piston rod so that you can prevent it from damaging. And after that, I want to talk about the geometric results. The geometric sequence model. So I'm gonna talk about the application that we use to get the calculation on this piston rod using the geometric sequence model. So the application is expansion increase proportional. It represents the material fatigue at higher temperature. It is short to say the geometric sequence is for extension by a fixed percentage from each cycle, because higher temperature accelerates material fatigue. So that is why we use this geometric sequence rather than arithmetic sequence model. But we also use both so that we can get the two types of result that we can get. So I'm gonna talk about the geometric results, which is with extension at cycle 15, the total extension after 15 cycles, and average extension per cycle. And we can also see the first cycle when the Tn is greater than 110, which is the limit, the extension limit of for this piston rod. And we can also see from the graph that have been plotted using Excel. This geometric model predicts higher risk due to accelerated expansion. Arithmetic model and estimate long-term expansion. So that's why we use geometric extension more than arithmetic. And then the safety limit is exceeded faster in geometric mode. Why do we need to use the geometric sequence model? This is important for engine safety and maintenance planning so that it doesn't go wrong in future. Alright, thank you. That's all for me.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Samsul Azharuddin. In this part, I will present the discussion and conclusion for Group 9 based on the result obtained from the arithmetic and geometric sequence model. The parameters used for Group 9 are an initial piston rod length of 104.0 mm, a constant expansion of 0.4 mm per cycle, a growth ratio of 1.004, and a maximum safe limit of 110.0 millimeters. For the arithmetic sequence, the piston rod expands by a constant amount in each cycle. At cycle 15, the rod length is 109.6 millimeters, which is still within the safe limit. However, at cycle 16, the length reaches 110.0 millimeters, indicating that the rod has reached the unsafe condition. In contrast, the geometric sequence shows proportional expansion due to repeated heating. At cycle 15, the rod length is already 109.98 millimeters, which is very close to the safe limit. At cycle 16, the rod length increases to 110.42 millimeters, exceeding the maximum safe limit. Although both models predict failure at cycle 16, the geometric model shows a faster growth rate. Once the safe limit is exceeded, the geometric expansion increases more rapidly, indicating a higher risk of failure compared to the arithmetic model. These results show that using a linear model alone may underestimate the actual failure risk. Factors such as operating temperature, material properties, mechanical stress, and design tolerance greatly influence the expansion behavior of the piston rod. In conclusion, the arithmetic model shows a steady and predictable expansion, while the geometric model shows faster and accelerating growth. Both models indicate that the piston rod becomes unsafe at cycle 16. This study highlights the importance of mathematical modeling in engineering application. By using appropriate mathematical methods, engineers can predict failure earlier, improve safety, and plan effective maintenance strategies. Overall, these projects demonstrates that arithmetic and geometric sequence are effective tools in solving real-world engineering problems and ensuring the reliability and safety of mechanical systems.